Okay, we'll go ahead and start. So first of all, I'd like to thank University of Illinois Chicago the ACM student chapter for letting us use the UIC Computer Science Lounge today. So thank you for allowing us to do so. So my name is Alvin Chin. My day job is I'm a research scientist at Discovery Partners Institute, which is an R&D institution within the University of Illinois system. And I volunteer here as the chair for the ACM Chicago chapter. And also as well, I also serve as the chair for the IEEE Computer Society Chicago chapter too as well. So we've done a lot of events together on very similar topics. So we're doing a joint event this evening. Thank you for those people here in person for coming, and also for you online too as well. And today we're going to have Xiaoguang Wang, who's a professor at UIC Computer Science Department, and he's going to be talking about Dapper enabling seamless program execution across heterogeneous architectures. So just a little bit about the Computer Society Chicago chapter. So we have our vice chair, Rajarshi Roy, who's from Discover. We have our treasurer, John Waltz, secretary, Dan Waterloo, and our young professionals chair, Narendra Venkatasan. If you're interested, we have our social media presence on Facebook, LinkedIn, and also on X. And also the ACM Chicago chapter. So like I said, I'm the chair. Our vice chair is Mark Temkin. Unfortunately, he couldn't come here today. We have our treasurer, Greg Newmark, who is recording this presentation tonight. And we have our newly communications chair that has started this year, Henrietta Dombrovskaya. Apparently, she couldn't be able to come here tonight. But she's the one that basically helps with ACM Chicago with communicating, posting our events on Meetup, sending emails and posting on social media. So we thank her for doing that. And if you're not on Meetup already, you can go to meetup.com/ACM Chicago. And you can find our previous events there as well as our upcoming events. Okay, so tonight's presentation is by Xiaoguang Wang. I'll now go ahead and put the microphone and give to him to speak. Just a little bit of housekeeping rules. So this is being recorded. And so we will send a copy of the recording and presentation afterwards. We will most likely put it onto our YouTube channel. And also as well, I know for some people like in IEEE or so requiring a professional development hour credit for 1 hour here. If you email me, then I can provide you that credit for that 1 hour. Okay, so Xiaoguang.
Yeah, all right.
And I'll change your slides. I'll change your
slides.
slides. Oh, a second, I'll change your slides. Second.
Is there another slide or?
Oops, sorry, no.
There's more.
There is, I have to go to the next one. A second.
You can introduce more.
Trying to find where my mouse is. Oh, okay, it's in here. Okay, so let me just. Let me stop sharing this one and get to. All right, here we go. All right. Here we go. We have that. 1 second, and I need to share this again.
Are you sharing this?
Yeah, I just need to find where did my pointer go?
I think it's this.
Oh, here we go. So I just share desktop 2, and there we go. Okay. All right. Floor is yours, Xiaoguang.
Sounds good.
Oh, yes, it's recording. Yes.
So how can we? I can just type the enter a or
No, you can just press the arrow.
arrow. No, it's not working. Up to.
Oh, no, I just have to move the heart.
Oh.
Yeah. So now you can just put the arrow. No,
Still
I'm
not
not.
working.
Click on it.
You can click on it, maybe. Oh, yeah, that's it. Just tap on it.
Oh, okay. Sounds good.
Yeah.
All right. Sounds good. Thanks for the introduction. And also thanks for coming here. Feel free to enjoy the pizza and soda. And one rule is like you have to ask a question if you eat one pizza slice. Right? Kidding. I'm kidding. That's nice. Okay. So my name is Xiao Guang, and I'm assistant professor at USCCS. So I'm mostly working in like system software and also software security. Recently working with like large language model to solve like system and security works. So the title here is quite scary. Enabling seamless program execution across heterogeneous instruction set architecture or ISAs. So you probably, I hope I didn't scare you when by saying that the instruction set architecture. So what is ISA, right? So in short, the ISA is a specification for software to access the hardware, right? So you use like x86 and you use ARM. So those are like commonly used architectures or ISAs, right? So here this program is basically try to allow you to do a live migration of your running process across the different architectures, right? So why we want to do this? One background is that like the computation process units are more and more heterogeneous. So we have already have multiple ISAs coexist on the market. And one of the reasons is that the end of the Moore's law have pushed the chip vendors to rethink their hardware design by, for example, more than like 20 years, like people are working on multi-cores, and right now people are working on heterogeneous cores, right? So I'm not sure whether you are familiar with some graph like this. So this is actually something called Smart NIC. So this is a network interface card, but with an ARM core and also some RAM on this board. So basically you will going to insert this Smart NIC on the motherboard with your x86 CPUs. So this is one of the cases that we have the heterogeneous CPUs coexist in a system. Right? This is another example. Is basically the Intel Xeon processor. There's a Intel Skylake processor from Intel that have this integrated FPGA inside the CPU. So FPGAs, you can consider this is a programmable hardware. You can write programs to this hardware. You can program this hardware. For example, you can program a RISC-V software core using this FPGA, right? So basically, you have your CPU is already heterogeneous in some sense, right? I also showed some news, like for example, this is a Xilinx Smart NIC. So basically, just like ARM-based coprocessors on this CPU environment, right? Besides Smart NICs, there are also something called a Smart SSD, right? So your storage also have like a built-in ARM cores inside this SSD device, right? So this is more for near data processing, right? So you want to do some processing near the data source where the SSDs you have, right? So given all these examples, and maybe we have some more, and especially in the AI area, we have like CPU, GPU, and also TPU cores coexist. And another example is probably the commonly seen is the IoT environment, like smart home environment. So we have multiple different kind of processors. Your laptop probably have x86 processors, and your phone is ARM processors, and maybe you have like for example other smart devices. So that's probably like a RISC-V or MIPS or different processors, right? So I'm pretty sure we already have the programs that manage to run on this environment. For example, using like message pathing or using like services, microservices, or other method. But here we don't know some other questions. So can we build like a software runtime layer on top of this heterogeneous CPU cores. And then we can possibly support some other more interesting applications. Like, can we relocate the computation from one device to another one seamlessly, right? And we don't know this potential benefit. For example, whether we have some benefit of saving some energy by migrating threads across x86 server or to a small Raspberry Pi, whether we can have some potential benefit of doing that, right? And also whether we can bring some security, because right now the process is not only running on one architecture and just have a diverse architecture underlying. So maybe the attacker is difficult to launch a particular attack targeting that particular architecture, right? So that's kind of the back motivation for this work. I think it's one of the kind of craziest project I've been working on. So basically, right here we want to build a software layer. The software layer try to hide the potential heterogeneous CPU cores under it, and try to provide a unified, uniformed interface for software running on top of this software layer. So this is something we motivate us to work on this project. So if I want to make a simpler or more straightforward example, we have like a pretty powerful server like this, right? You probably have seen this kind of server all the time in the data center. And if we have a running program, this server program that's running in the daytime, handling a lot of requests, right? So this is happening all the time. And then we don't want to have this server running on this powerful machine, but can we like migrate it to the like Raspberry Pi board at night when there's no people is accessing this service, and we shut down this server. And once we need it, we launch the server and make it back. So can we implement something like that, like leveraging the heterogeneity of the processor cores or doing this? So we want the process to be seamlessly migrated between these two machines, right? Any questions? Or no? Good. Yeah.
Yes, just for clarification, the software layer isn't going to function as something like the JVM, right? We're not like interpreting our JVM somehow.
Right. So the question is like, what's the software layer looks like? Is the software looks like a JVM or something like, right? So actually, we are not using a JVM. We are trying to we're targeting the binary, the ELF binary. So like vanilla application executable code running on top of this layer, right? Yeah.
Yeah. Let's see here. Oh,
sure. Okay. I think you already basically answered a very related question, but do you think that this would be made easier if we were willing to restrict ourselves to some sort of high-level language environment? Has that already been done?
Good question. Actually, no. So we look into this JVM-based migration, but it's very hard. The JVM itself is very hard. Probably we didn't find the correct person to work on this project. We tried this JVM like migration of the program state migration. We tried that, but it's very hard to understand what JVM looks with what's inside JVM and do the modification.
It seems intuitively, I would have thought that additional abstraction would have helped.
Yeah.
Interesting. I would have thought that would have helped. Interesting.
Yeah, but actually it's kind of difficult to modify the JVM to save the program state of JVM and then restore it on the other side. It's relatively complicated.
So it's maybe even easier if they're well, it seems like they'd be less competitive. Maybe for some reason it's easier at a layer closer to the hardware. Or is it just also difficult, but you know it more?
Yeah, we can talk about that. We can talk about how this works, right? So that's good questions, right? So I think we have I have some discussion about those the requirement we have, right? So here we are targeting vanilla ELF binary. So basically, you compile the native program running directly on your CPU. It's not a managed language like JVM or Python running in a JVM virtual machine, right? So here we are targeting those programs natively compiled like ELF binaries. So in order to do this process migration, right? So what we have to do? So here we want to make some simple assumption. For example, we assume the binaries are compiled from the same source code, right? So we'll assume the binaries have the same semantic. So basically, if we have the same source code, we can use cross-compiling techniques to generate the code for x86 architecture and for binary for ARM architecture. We can generate from the same source code. You probably have been working on that in some of your research project or other work, right? So that's kind of first thing we need to do. The second part is like, how can we convert the program states across the different architectures, right? So on x86, you have your program context. We call it program context, right? So in the operating system, we probably learned that. So basically, you have your REX, RBX, all these register values. That will be completely different from those register values on ARM, which you have like X0, X1 to X29, I believe, something like that, right? So they are completely different. How can we convert this program state across these different architectures? And also, third question is like, if we migrate the process across different architectures, how can we provide a unified view of system resource? For example, your virtual memory. How can we have the same virtual memory for different machines with different architectures, right? These are all kind of unknown questions, and also we need to address these questions, right? So here is our kind of work with my colleagues in Virginia Tech or researcher from Virginia Tech. So it's called a Popcorn Linux project. So here we have a simple idea of that converting the source code using a special customized compiler, and we compile the source code into two sets of binaries, right? So another part is that we have something called the multi-kernel OS. So we have each Linux kernel running on each processor, right? So you have, for example, you have different 3 ISAs. We can have 3 Linux kernel running on top of that, and this Linux kernel, 3 Linux kernel communicate with each other and to hide this heterogeneity for the running processes. It's pretty complicated, but I hope I can give you some answers for doing that, right? So, okay, then let's come back to the first question. Oh, wait. Okay, so how can the program state be transformed, right? So the program state, we can say this like binary code we just mentioned that we just compile from the same source code, and we can get this same binary assembly code, right? And the second part is basically the register memory stacks and maybe some other components that differs between different architectures, right? And that's the major part of the question, right? Any questions? Good. Any questions? No. So here, basically, we want to convert the registers, memory stack, and other architecture-related components between these different architectures, right? So how can we do that? So here we have some background. So we actually leverage something called the LLVM intrinsic. So LLVM is a compiler framework. It's open source compiler framework similar to GCC. So this is, I think Apple is using LLVM. So what is intrinsic? Intrinsic is kind of like a helper function in the compiler. You can insert this helper function, and this one is going to generate some code. For example, in LLVM, how are you going to insert the libc cost, like a memory copy, for example? So the memory copy is one of the intrinsic in LLVM compiler. So here we use another not commonly used intrinsic function. It's called stack map. So we insert something like this, right? So the LLVM experimental.stack map. So we insert a call, intrinsic call, and we can get some live value information or live variable information, right? So we leverage this stack map to collect some architecture-related information, right? So what is the live value? Live variables, I think I show it up here, right? So those live variable. I'm not sure whether you covered in you kind of had this experience in a compiler or program analysis. So a variable is alive, meaning that this variable have some downstream use cases. So you're going to, at this point, for example, at this point, if we try to get live variables, basically we are getting some variables that's going to be used in the future, right? So maybe this is a better example. I'll show you up here. So we insert the stack map intrinsic at the beginning of this add function to add A and B. We return A and B, A plus B, right? So why? So here we basically A and B are live variables. Why? Because we're going to use it like return A and B, A plus B, right? So basically we use A and B after this entry point of this function. So at this point, if we instrument LLVM stack map intrinsic, we will get something on the right side. So you can see something on the right side. We are showing that there are like function 0 and 1, and we have some cost at 0. And here we are showing like location, size 4 and size 4, meaning that A and B are both 4 bytes in size. And also here, the interesting part is next. It's like in register 3 and register 14. So basically the compiler telling you both A and B are live at the entry point of add function because they have the downstream use cases of A and B, right? And also at this point, this A and B are stored in register index 3 and 14. This is kind of like index for x86 architecture. Probably it means like RCX register or like R11 register, right? So those kind of x86 specific registers. So similarly, if we generated the binary for the ARM side, so A and B will be generated to like register 20 and 19, right? So something here. The mouse is not ready to use. So basically, this A and B will be live and stored in register 20 and 19 on ARM architecture. So our ARM architecture is probably like register X20 or X19. So by generating this stack map, so we have the runtime information of the registers. At a certain point, we call it a semantic equivalent point. So at this point, both x86 architecture and ARM architecture, they are having the exact same semantic, basically both at the entry point of the add function. And we get the live value for those variables. So we can easily transform the values in the runtime, right? Any questions before I move forward? Yes.
So are you compiling for multiple architectures at the very beginning?
Yes.
So you're compiling for multiple architectures at the beginning, and then your source code then becomes, 2 or 3 or 4 times bigger because you're carrying along all the different architectures with it.
Good question.
Or
yeah.
you're doing it at runtime later.
Actually, the source code, we don't modify the source code, but we compile the source code into executable binaries, like ELF binaries, right? So in binary, we have the special ELF section called stack map section. So we have this metadata inserted in executable binaries. So that's actually binary size increased.
Okay. That's what it looked like.
Yeah.
Just clarifying.
Yeah.
Okay, thank you.
Of course. Mm-hmm. All right. So this is one of the part we have. So once we get this executable binary, we launch it. We execute it, this binary. We get the processes, and here we have this multi-kernel architecture that's allow us to do to provide a uniform virtual memory, or it's a software-based distributed shared memory, right? So basically, it's a shared memory across different machine nodes. Right, this is similar to like a NUMA. You have NUMA architecture. You still basically each NUMA node have their local physical memory, but you can still provide a virtual memory on top of different NUMA nodes, right? Yes.
But these are different, like architecture CPUs, right? So it's just
Yeah.
RDMA.
Right. So we implement this distributed shared memory with it's basically software based. Like if you heard about like MSI protocol, like modify, share, invalidate. So you can implement this in the kernel page table handling routine. So basically, you can handle you can use page table handler to provide the distributed shared memory. Does that make sense?
User fault testing.
Yeah, that's a user space implementation. Here in this project, we implement this page fault handling all in the kernel, basically modify the kernel page fault handler. Yeah, good question. All right. So we have a prototype of this. I think there are more details. I just try to give you the the high level idea and key idea of this approach. So we have to build a prototype using two servers. We ran it on 2 servers and connected with this MetalNext ConnectX InfiniBand. So we support RDMA, support RB verbs. And we modified the kernel, Linux kernel 5.2 to support program state transformation, synchronization, and also the page and the virtual distributed shared memory, DSM, right? So basically, we have the virtual memory layer, and we evaluated on using some benchmarks. So here we just show you some numbers here how bad the performance or how good the performance. So we have for example get PID system call. So that's like a very the simplest system call in Linux probably to return the pin number of the running process. So if we run the PID locally, it's like 0.747 microseconds. And if we executed this on the remote kernel node, it takes like 18 microseconds, right? So it's kind of quite expensive. But if we compare to like a raw network ping pong, this benchmark, so I send you a package and return. So this is actually 17 microseconds. So it's pretty fast. And there's another comparison evaluation, which is a ping latency. So you send it from the user space and then return this package back to the other node, the other node. So this is 100 something microsecond. So actually the remote get PID is much how to say that, short than even a ping command, because we don't have the user space to kernel context switch. We directly have the kernel communication, kernel to kernel communication. So we also measure something like the ISA switch, the architecture switch. So basically we ran the program and we switch the ISA to another machine. So this raw ISA switch is 500 microsecond time. It's kind of reasonable, right? Kind of pretty decent. Yes, question?
So,
Mm-hmm.
So for remote get PID, was that between machines running the same ISA?
2 different ISAs.
How? So that was like 2 parts of the. No, I'm not sure I understand in what way the get PID was remote. There.
Right, good question. So basically, if you consider each ISA, each architecture, we have a kernel, right? Linux running on there. If we are not executing the get PID on this kernel, we are executing PID on the other kernel. That's called a remote get PID.
That makes more sense. And you're measuring, when are you starting measuring and ending measuring this latency remote get PID? Is it starting in the user program?
Right, that's a good
and then ending
question.
in the program?
I think that's in the user program.
Okay, that it doesn't make sense to me that it could. Well, I don't know all that's involved in the ping latency, but it seemed like the major thing there was simply
user to kernel connection.
Yeah,
that's a good question. So I cannot remember the details of this experiment. I also like raw network ping pong this experiment. I cannot remember the detail. But
I mean, get PID was also very fast, and I assume that was user to user.
Right. Yeah, so probably the reason. I think that's probably the get PID very fast somehow, right?
So
probably.
ping latency is just really slow for some reason.
Yes, right. But I think the ping probably have to do some package processing. I think that's kind of the reason, I believe. Yes, but good question. So we also have some real real application evaluated. So we use like NGX web server for this cross architecture context switch IC switch. We call it IC switch, right? So basically, we here on the x-axis is like the probability of this IC switch at each point of this like NGINX web server. On the y-axis is like the normalized performance compared to a native NGINX execution, right? So here if we evaluate it using like Apache Bench, like sending a lot of the HTTP requests. So if we run this web client and web server on the same local network, so actually we get a very, very bad performance. Like for example, probably 10 to 15% of the performance compared to the native NGINX execution, because the IC switch is pretty expensive. And also we have this, for example, one request, we will have at least one like IC switch. But if we if we configure for real world scenario, like for example, we try to use like a edge computing scenario with a latency of 10 ms network latency. So we are having we're reaching like 80% of native performance from the throughput, right? And if we are using like for example, cloud computing scenario, this is done like several years ago. So I'm pretty sure cloud computing and edge, their latency is much smaller than this number. So if we having like 14 ms network latency, so we are reaching like 90-something% of the native throughput, right? So that's kind of the evaluation on real world applications. Yes, questions?
So I understood from the previous slides that there was this LLVM intrinsic you were using to map from like registers and that sort of thing from one architecture to another. But here, we also have to like transfer the state of open TCP connections, right?
Right. So here we actually read. Okay, that's a good question. So we migrate to the other machine nodes for computation, which is executing locally. Computation memory just executing locally. But for some system calls, we have to redirect back, because otherwise, in this case, we cannot handle some like for example, socket system calls. We have only allow the first node to handle the socket system calls.
Oh, okay. So sometimes there's an extra price, a couple extra.
Yes.
Okay.
Yes. Yeah. Good questions. All right. So issues, right? So we know this is multiple issues. So for example, one issue is you mentioned that we have to handle the system costs. This redirection, this costly, and there's some other issues. For example, like it's very heavyweight. We modify the kernel, right? So we actually have make some attempt to upstream the top kernel to Linux kernel mainline, and you can find the Linux kernel mailing list link right there. So we make the attempt, right? So this people from the kernel community, they send us some advice. It's super complicated. It's you modify the kernel page fault handler. It just like make it not that looks very good. And also, it's very difficult to formally verify it, so make it bug-free, right? And right, so that's kind of the situation for this work. So can we provide a more like lightweight solution to solve this problem? So the next work is actually our we call it lightweight architecture and program state diversification through via process rewriting. So we have some other ideas based on this high-level ideas, right? So we want to remove the OS, the kernel modifications. We don't want to modify the kernel, right? So the overall idea is like this. So I'm kind of motivated by this scenario. So consider we have two program binaries already compiled from the same source code. They are semantic equivalent, and we run it on x86 cores and run it on the ARM cores. We run the two binaries on two cores. We got two threads, right? Two process or whatever you want to call them. At the same time, at the same point, we want to checkpoint this process into process images. So a process checkpoint is like, you can consider it, we take a snapshot of the running process. We freeze it, so we get like some process images, right? And then we've got two process images. And then if we restore the execution from these process images, we got these two threads, and they are supposed to need to the same thread, right? So this is checkpoint at same location, right? That makes sense? Good? No?
And that, what are we achieving here?
What?
what did we achieve on the exercise?
What are we achieving here? Yeah.
Yeah, in this exact example, I
Yes. I'm not achieving anything from this example. Good question. All right. Okay. Yes. Yeah. Sure. Absolutely.
Okay. The memory, is that stored in the read-only memory at this point when they checkpoint it, or where is it stored?
Good question. So we can checkpoint the running processes and save it to files on the disk.
Okay.
Does it make sense?
Yeah.
Okay, good.
That's all.
Yeah. Great. Great questions. All right. So meaning you're not lost. Okay. So here, once you understand that example, so let's think about something differently. So we have the thread running on x86 core, and at a certain point, we checkpoint to a process image like this, like yellow bar, right? The rectangle. This is a process image. You can consider that, right? So if we can have a tool that can convert the process image to a process image of the ARM format, right? So this is familiar. Like you remember that from the previous slides. There are two process image checkpoint at the same location, and if we develop a tool that will checkpoint a process image at one point, and we can convert it to another process image running on the ARM format. So the process images are like files, just files, right? You can develop a tool, and then we restore the execution. So basically, we are line migrating a process from x86 core to ARM core seamlessly, right? That makes sense? Questions? Good. All right. So this is our idea for this work. So basically, can we rewrite a running process to enable a line migration across different architectures? So that is actually the core part of our work. So we basically designed the approach to rewrite the running process, to snapshot it, and rewrite the process image and restore the execution on the ARM core. So we want to achieve several goals. For example, efficiency, we want to make it very fast. We also want to have minimal service interruption time. We want to do line migration. And we also want to have minimal or no OS modification. We don't want to modify the OS kernel. Right? That's a key idea, right? So how we do that? So luckily, we have a fantastic project from the Linux community. It's called Linux Checkpoint and Restore in User Space, or CREU. So this is a very mature technique used in a lot of the production environment, I believe. For example, container line migration or process migration. I think people, if you line migrate a container, you basically use the CREU under the hood. So the key idea is that we can freeze a process or container and checkpoint its state into the disk file, right? So basically, we can get a disk file. So this is basically the format of the snapshot. And we can restore the file to a process. And once we get the file, I can move the file to another machine, restore it, and then you get a running process seamlessly migrated there, right? This is already commonly used there. So this is a CREU website. Feel free to visit their website. Fantastic project. So for CREU, they can only support homogeneous migration, like x86 to x86, ARM to ARM, RISC-V to RISC-V. But here in our work, we developed this tool we call it Dapper. I'm not sure whether I pronounce it correct, because when I have it, I always pronounce another word. So the key idea here is that we still compile the application into binaries. And we can checkpoint the process and then check the process into a file, and then we can rewrite the process image, rest the file, the checkpoint file, and then we can either move it to another node, ARM node, and restore it on the ARM architecture, or we can do some other work, like for example, we checkpoint the running process, we can rewrite the libraries. For example, we can live update the shared libraries, right? So for example, if you have a buggy version of libc, we can checkpoint the program, rewrite this process image an upgrade provided with updated version of libc, right? So this is actually ongoing work by a student working with me for this semester. Right? We have a class called Linux kernel programming class, and one of the students is working on that. I think he already supported several upgrade version of the library. For sure, we have limitations for this approach, because if the modification is too big, we introduce new function, there's some address change. That is out of our consideration. But I think he told me like we can support like 50% of versions in a few libraries, commonly used libraries like libc or something like that, right? Right. So we also have some other ideas using this potential technique. So a little bit details, right? So here how we did it. So we implement this prototype by extend a tool in the Creo project called Create. This is Creo image tool, like called Create, right? This tool only allow you to view the checkpoint process. So basically, this is a Python-based tool. I think the new version they have a Go-based tool. So basically, this tool allow you to check the process snapshots, those files, and give you some information like what is the PID of this checkpoint process? What is the name of this one? What is the memory map of this checkpoint process image, right? So what we intended by adding the rewriting capability to the Creo, the process image, right? And we also developed like a runtime that help us to pause the process at certain points. So we mentioned that we want to pause the process at point, like function entry point. So at this point, we can make sure the translation is smooth, right? We don't have any potential issues, right? So we support multi-threading with a per process monitor, and we can with this ptrace-based tool, we can pause the process all at this kind of nice locations, right? So we implement that using by extending Create tool and also like develop this ptrace-based monitor, and we evaluated on something called Cloud Lab. It's an education cloud, so everyone can feel free to use it if you are like with a university. So we have this environment set up using like this two version of instances, and we have the infinite band connection. We also have a local deployment. So basically, we have like an existing server and several Raspberry Pis, and this is a configuration. So with we have a demo here. I know it's kind of boring if you didn't follow it. So we have a very simple program showing up here on the right side. It's a very simple program. It's just like a main function, get the PID, and then call loop. And call function one, and function one, call function B, and in function one and function one and function two, they have some sleep. They have called like system uname -m, showing the architecture of the running process, right? So if you execute this loop demo on x86, you will see something like that: 0, 0, function one, function two, function one, function two, something like that. Very boring print, right? Okay, so this is actually a demo. I hope I can. This is hard for me to play it. Okay, so I started from the x86 server, from the Cloud Lab native. We don't modify the operating system. You see, this is like Ubuntu 5.4 generic, right? So this is a default Linux kernel. And we also have it on the ARM side. And as you can see, this version is slightly different, but it's fine. One's x86 server, one's ARM server, they're connected. So we start the program on one architecture, and then the loop is kind of printing this boring messages, but it's showing the function one, function two on x86. And here I have a script to checkpoint, rewrite the process, and copy the rewrite process image to ARM. I know this is a little bit fast, but sorry. It's a little bit fast. So here is actually the rewriting script to do the dump and rewriting. And where is it? Where are we? Okay. Here we got a new like AR64 basically rewrite process image, and then we can restore the execution with Creo, just called vanilla Creo restore. We restore the process. Oh, what happens? Why is like this? Okay. So yeah, right. This is a key part. So once we restore the process, we can see it's actually stopped at number 4, and then we started with number 5. It's the live migration of running process on heterogeneous architecture with user space tools. We don't modify the kernel. Any questions? Good. Yes.
When you stop executing and you migrate the process image, where is the process image stored? Is it on a shared drive between both systems?
Oh, good question. Actually, no. So we checkpoint on the x86 side, and you get the file. We write the file, generate something called ARC4. And here we had just use regular SCP command to copy it to another server.
Okay.
Yeah, we can use like NFS, have the same shared
Using
storage,
NAS or something.
but we just use SCP for the demo.
Okay.
That's good. Yeah. Good questions. Oh. So we here we evaluated, actually we use like HPC benchmarks, MTB, NASA, Parallel benchmarks, and HPC applications. And actually if we write the process image on the x86 server, we are having like end-to-end time overhead of 600 ms, right? So if you can see this breakdown of the numbers, so actually the checkpoint and restore are quite fast, but then the recode, basically rewrite the process, that's kind of slow. And also the SCP, which show SCP, basically we use SCP command to copy the images, that's kind of slow. So, but overall, it's very reasonable number. And notably, on ARM side, it's a little bit slow, but we can always do the recoding on the x86 server, right? Because this is architecture, recoding part is architecture independent, right? You can always recode it on the x86 server. So another very interesting thing I want to mention is that we also support lazy migration. So why is this an issue? So it's considering if we have the application that consume a lot of memories, like Redis key value store, this is a key value database, right? So in-memory database. So if we created a database of 1 GB, for example, you can see on the right side. If we try to checkpoint a Redis server that have like 1 GB of memory, it's actually very slow to copying the process images between the two machine nodes, right? So the 1 GB of the file copying is very expensive. To solve this problem, so we extend the CREU lazy migration. This is already implemented by CREU, and we implement that for the heterogeneous version. What we have is that we checkpoint a small part of the program. We copy that small few pages to the ARM side, for example. And then once we start it, so for sure we cannot successfully execute it without doing anything. But what happens is that we can leverage this migration and we can start it whenever there's a page fault, wherever you try to access a page, there are page fault. The page fault handler retrieve the page from the original node on the fly. Like lazy paging, lazy migration. That's the idea of this. So by using lazy migration, we can only copy a small portion of the program. You can see on the right-hand side, I think the mouse is not very easy to use, but it's somewhere here, right? So we can significantly reduce the overhead from like 30 seconds to 2.5 seconds, right? So with the lazy migration approach, we don't have to copy everything for one time. We copy it and then page fault handler retrieve it. Yes, any questions?
If you need to pull more data from the other system, how would that happen? How would that work?
Right. So actually, we need to pull the data because we have a page fault, right? We try to access memory, but it doesn't exist. We have a page fault. So in CREU, there's a mechanism called the user fault FD, user space page fault handling. So when we have this situation, we have a page fault, and then we retrieve that page. The page fault handler retrieve that page from the original node. The original node, there is a page server serving the pages to the destination
So it
node.
would send the entire page, and then it would do the program. And
Yes.
then, continue. Okay, I see.
Yes. Yeah.
Right.
Good.
Thank you.
Good question. Yes. Any other questions? Good. Good. All right. Cool. All right. So we also want to evaluate the efficiency, right? So here we have like a Intel x86 server and 3 Raspberry Pis, the small board. So we're sending a queue of HPC workload to the Xeon server, and then we can dynamically kick or migrate some processes to the Raspberry Pi. So with our approach, we can save a lot of for example, we can improve the energy efficiency by calculating the number of jobs per kilojoule, I believe, right? So by improving to up to like 39% of energy efficiency. And if you only look at the throughput, we can still gain like 30-something% of throughput. So by just dynamically kicking those threads to some additional cores, we can significantly improve this whole system of energy efficiency. Yes.
What do the acronyms mean?
What that?
At the bottom.
Oh, EPMG. Okay.
Yeah.
So those are so we're using like NPV benchmark. So those are like test applications in that benchmark. There are like probably 8 applications of that. So those are like computation intensive HPC applications, right? Cool. All right. Challenge and limitations. So it's pretty crazy idea, and we also face challenges, and we also know some limitations, right? So one challenge is that we cannot support arbitrary application like migration. Why? Because commodity software is not designed for line migration across heterogeneous assay, right? So for example, if your software has an inline assembly code, so we cannot handle this. You have an inline x86 assembly, we cannot have a solution to convert it to the ARM on the fly. This is out of our consideration. And also, the software stack is pretty complicated. So if we make some bugs in the transformation logic, so a single mistake can cause translation failure, right? So for example, if we forget to translate a particular register, and very likely you get some failure, right? So this is kind of the limitation of this work. And okay, in summary, so here I just try to give you this general idea of our work in exploring how can we manage software runtime on heterogeneous architecture. And we have the multi-kernel OS approach, and also have the process checkpoint rewrite and restore approach. So this is a website, a Dapper project, GitHub.io. So you can find the demo or source code or other documentation or papers there. So we also want to acknowledge our sponsors from Office of Naval Research, NSF, and also the KC, Google Cloud, those kind of sponsors. And I also appreciate all the ACM Chicago chapter for organizing this fantastic event. And thank you all. If you have any questions, I'm happy to answer. Yes.
Okay, great. Now we're going to have some questions. So, Greg?
A couple of things occurred to me that maybe are good or bad. The ability to switch architectures, say you suddenly find out your x86 processors have a floating point math bug. You could just switch all your code and run them on ARM while you figure it out.
Actually, that's a very good question. Actually, that's our limitation. So I don't think we support like a floating point registers translation at the time when we developed this. It's one of the limitation. So we don't have a very good solution to translate the floating point registers. That's the short answer.
And my other question was, I don't know how complicated the software you've tested with, but I would think that having this additional rewrite process would make debugging a lot harder, because you're like, did I make a mistake in my code, or is the mistake in the translation?
Right.
And what was your experience in was it obvious when it was in the translator versus the code, or was that a difficult?
Right. That's a very good question. I think that's a very good question. So actually, if this is a bug in our translator, for example, we can immediately notice it, because when we restore it, it fails. So if you run this for a long time and there's a bug, this is not likely to be something logic in our translation, because our translation is just like stack or the execution context. It's very easy to detect.
Is there any questions from online? You can unmute yourself and say your question.
Oh.
See what's in the chat too.
Yeah, I cannot find it. It's difficult.
Yeah, okay, here we go. Okay. Okay, that's quite a bit. Okay. First question from David: would the Java VM approach fit in here?
Good question. This is being asked again. I think that's a very great question. So we try to support JVM or Java application like migration across different architecture, because I think we thought that JVM is a perfect layer hide a lot of heterogeneity, but we didn't find any solutions to checkpoint the, for example, JVM program at the JVM level, right? So if there's a tool, that would be much easier. But at certain, I mean, at that time, we don't have enough people because we are small, still again like small research group in the university. We don't have a lot of students to continue working on this project, and we didn't have the JVM version working. But I'm hoping if you have any resources on JVM, just we can reach out or.
Okay, thank you. Question from David. How does this compare to what Transmeta was doing before they went out of business?
Actually, I'm not aware of this Transmeta. So do you provide that or not?
I actually have a Transmeta laptop at home.
Oh, okay.
But it was a processor, a CPU
Uh-huh.
that kind of simulated or virtualized Intel, but it was running on a different architecture internally.
Is it like a QEMU? Those kind of
No,
not like
it's
that.
a hardware device.
Hardware
It's from,
device.
like, 2000.
Okay. So I'm
And
not
they weren't
aware
very
of
fast,
that.
and they didn't last in the market.
Right, all right. I mean, I have no idea. I have never have it. Like as you are saying, this is a CPU hardware translator, translate instruction from Intel to ARM or something like that.
Yeah, I'm not really, it was their own thing.
Okay.
Probably ARM-like.
Uh,
I think it was, I thought it was VLIW, very long instruction word. So they
Okay.
did they didn't I think that VLIW does the instruction level parallelism like at compilation.
okay.
So I don't know if it's similar to other things.
Right. Is this translation on the same machine or is translated across different machines?
Yeah, I don't think it really
Okay.
has much to do with across different machines.
Right.
I
Right.
don't know if there were other architectures that Transmeta was
Mhm.
implementing, but I don't think it was at all about migrating a given
Right.
process.
Right. So we are having some. I think there's some software approach like a QEMU. You can translate, or like for example, similar like Windows. The Y, like you can run a Windows application on Linux, something like that. That's more software based translation. But in our case, we are just doing native execution migration.
Yeah, I think that's something.
I just had a question I thought of because you mentioned that you can't properly migrate like floating point unit state, which I think makes sense. And I remember reading that the Linux kernel actually avoids using hardware floating point operations for that reason. So they switch to user space. They can't. Well, the user program switches to kernel. They can't guarantee that they've like backed up the user program CPU state. But does that mean that also this doesn't support like GPUs? I don't imagine at all. They have some internal state as well.
Right. We don't support GPU at this moment. So we try that. I think GPU, the program states transformation is much difficult than like a CPU state transformation. So we tried, but we didn't get a very good result.
Okay. Thank you.
Okay, great, thanks. And I think there's another question. We said this one already. How does this compare? Oh, how do you deal with big endian and little endian differences?
Good question. So we don't deal with that. We are supporting, I think ARM x86 is all like little endianness, right? So we don't even RISC-V, we support x86 ARM RISC-V. They are all like little endians, I believe. So we don't have this. We didn't solve this problem. So we just having the commonly used architecture. They are same endianness. Yeah.
Okay, thank you for that. How do you deal with structure padding differences between architectures?
That's another very good question. So, so we actually have one situation. So if you have a data structure in the application level, normally we will have the same layout normally. But we have one case I remember that's our data structure in the libc. I cannot remember which libc call. So basically, that's data structure on the two sides are different. So we had that issue. Is it like epool or something? So there's a struct that have different padding. We only have that one issue, as I know. So I think at that time we either patch the libc, the master libc we're using. I think that's our solution to solve this problem. Yeah.
Okay, great, thank you. We see here. Oh, that's Robert. Do you have to checkpoint at specific points? When running a function, some of the variables are in registers and some are in memory.
That's a very good question. So we don't have that requirement. So but we do instrument intrinsic at the function boundary. So why? Because we cannot migrate at any point. The simple reason is that one C code can be translated into, for example, 3 lines on x86 or maybe 7 lines on ARM. So if we are doing this in the middle of it, so we are definitely in trouble. So we want to make it simple. We just have it a checkpoint at the C level, like a function boundary. Then the other question you're asking is like, do we need to consider whether they are the same number of the values on the stack or on the in registers? So this is a very good question because some architecture have more general purpose registers, some architecture have less number of general purpose registers. So that doesn't matter because stack map can tell us if the values, if we don't have enough general purpose registers, we can emit those values on the stack. So this information are still in the stack map. We support the values on stack to registers or register to stack rewriting. So that's being supported.
Okay, great. What else do we have? Okay. There are some difficulties with remapping those between architectures. There is no guarantee that the different compilers would map their data in the architecture in the same way. Like just as a comment there. And sometimes compilers optimize variables anyway. There is no guarantee that the same variable set exists on both compilers. Do you have to turn off all optimization?
Right, that's a good question. So I think we turn off the optimization to make it just much simpler. So we didn't consider anything with like O3. Sometimes it's really, really complicated once you have a higher level of optimization. Yeah, that's down there.
Okay. And with lazy migration, are memory pages converted but not transferred until faulted in, or not converted until faulting shows a need?
Lazy migration, if my understanding is correct, so lazy migration is that we don't have those pages copied to the destination node. We let the destination process to start. And for sure, there will be a lot of pages need to be like how to say that, handled, right? So basically, whenever there's a page fault on the remote side, on the destination side, we try to handle this page fault by retrieving the page from the original node. That's the case. I'm not sure whether I make it clear.
Yes.
Well,
Just to clarify, I think
yes.
if you got your example of like a gigabyte of memory, but you're not translating that, that's just memory that you're bringing over. Or is that
Right.
yeah, it's only the program state that's
Yes.
being translated.
It's only the program state need to be translated. Other data, in-memory data, we just keep it. Right.
Okay, yeah, thanks for that
Oh,
clarification.
there's some question.
Oh, question? Yeah, sure.
Follow that.
What's the line between program state and other in-memory data? To me, that seems very fuzzy.
Right. So in-memory data, you can consider it like, in-memory database. The application data, we don't need to do the translation, right?
So
We need
is
to.
this a decision we make on a per application basis? Like we only have to like eagerly move in, translate some of it, and we need to know that the application has the same
Right.
binary format for the rest of the data? Is that what?
No, actually, the program state data is you can simply consider it as registers and a stack.
Okay.
So other data like on heap,
Okay.
allocated with malloc, or mmap data, we just keep it the same.
Okay.
Does it make sense? Yeah.
And then for the Redis example, when you have to fetch for a page fault, are you saying that the original source still is running and has access to those page faults?
Right. So the original node it's not running, it's freeze already. But there's something called page server, it's another process. Listening a request from the destination node. Whenever there's a destination node and a page fault, the page server going to retrieve the page, send it to the destination, and then clear that bit. Basically, this page is already served. Once all the pages are served, the page server can disappear, right? that make sense?
So there's a third person, third computer.
Yeah, that's called the page. I think this is from the Creo, vanilla Creo that already have this page server capability to leverage it.
All right, let's see. Set that one. Yeah, VLI belong instruction word, transmitter processors. Okay. Yeah, that's it we have
Okay.
from online. Any other questions here in person before we end? Okay, well, if not, thank you, Xiaoguang, for your presentation. And then I'll just go ahead and end off here. So let me first of all. Oops. Yeah, thanks. Let me see. I stop sharing here. I'll stop sharing this one. And 1 second, just return to. Where's my thing? Okay, here we go. All right, just bear with me for a second. Where did my PowerPoint go? Oh, how come this is still going? All right, let me go to this one.
Sometimes screens dialogue up in front.
It's not it. PowerPoint. How is it doing this?
Can you just hit escape on that screen?
Let me see here. Acknowledgement. Okay. Okay. This one.
Zoom still going?
Oh, how come I can't see mine? Oh, okay, I know why. It's in here. Okay. Sorry. The problem with multiple screens. Okay, so that's in. We got this already, but I need to share it now. Share desktop too. Okay, great. So yeah, so thank you, Xiaoguang, and sure, yeah, thank you. Okay, yes. So our next event actually is a workshop. It's on next Friday, April the 11th. And actually, I'm the one who's going to be hosting this workshop as part of Discovery Partners Institute in conjunction with ACM Chicago and also ACM SIG Chi, the Chicago Chi chapter. So CHI stands for Computer Human Interaction. And it's going to be a workshop from 1 to 6 p.m. It is both online and in person. So you don't have to attend for all of it if you can't. It's going to be held at my office at Discovery Partners Institute, which is on 200 South Wacker Drive, just across from the Willis Tower on the 4th floor. And it's in classroom A. More information, just go to our meetup webpage, ACM Chicago, and then you'll find the next event there. So you can register either online or in person. Basically, what this workshop is trying to do is that it's trying to look at how we can use diverse connections through mobile social networking. So basically, what I will kind of present there is that some of the work that we've done as to how we can easily connect people from offline to online. So we developed a kind of an app or so where we can record these kind of like proximity interactions that people have with each other at particular in-person events, and helps you determine who are the people that you were together with. Because many times you go to an event and you forget to add that person to your LinkedIn or so, you forgot to get a business card, you forget to link the scan the QR code. So this is a way where you can just go ahead and go throughout your particular event, and then at the end it will tell you, hey, did you know that you met with Greg here, and did you at some particular different places in the event. So that's something that we have, and we're actually going to have a demo that you can also try out too as well. So have a look at that if you're interested. And this is supported. We thank ACM SIG Chi. They gave us a development fund grant to support this work. And yes, so we always are looking for other speakers for our ACM Chicago events. So if you have an interesting work, that you want to talk to other people, get some comments, get some, feedback. It's a great way to, help your speaking capabilities. You can contact vice chair at chicagoacm.org or chair at chicagoacm.org. And we have a whole bunch of, videos. We need to update the ones from last year that are on there, but you can see ones that we've done all the way since like 2022 or so that we record. And actually, Greg here is recording right now on the camcorder. If you go to bit.ly/ACM Kai video, you will find a list of all our videos there, and we're going to try to update those with the latest ones that we have there. So if you kind of like subscribe to this channel on your YouTube, you will see when we get the newest one there. And we had a lot of speakers in ACM Chicago. We got a particular good speaker from the Argonne National Lab, the Leadership Computing Facility. So they're the ones that, they have the, now is the world's fastest supercomputer called Aurora, which I got to get a chance to actually have a look at from the outside. It couldn't let me go inside, obviously, but it's quite a thing, yeah. And of course, you're always looking for volunteers, right? So ACM Chicago, we don't do this, we don't get paid. This is something that we do because we're passionate about computing and passionate to tell other people about it. So we're always looking for more, volunteers. And it's a really great way to like bring something back to the community and use your skill sets. And you can also learn new skill sets. So for example, we're looking for people to do stuff with writing, for planning, videography, audio editing, networking. Because, as students, networking is very, very essential, right, to your career in order to determine, what you're going to get as your future job or people that can help you with your particular research. So this is very good networking opportunities. And of course, help build this interest in computing for everyone. All right. So thank you, everyone, for joining online and in the person. And like I said, this is being recorded. And if you need a professional development hour credit for tonight, you can just email chair@chicagoacm.org. So if there's nothing else, then thank you, everybody, and enjoy your evening.